Hello, ladies and gentlemen. In this video, we are going to be putting everything we've learned so far regarding systems of equations, systems of inequalities. We're going to be putting that together to do a little process called linear programming. Now, the big thing that we want to do with linear programming is we're going to be presented with a big word problem, and we want to figure out how to maximize or minimize a situation. So here's some vocab. If you need to pause and write things down, by all means, go for it. But the one thing that I really want to kind of key in on is the whole concept of maximize or minimize. That is our end goal, and that always ties back to what's called the objective function. The objective function is going to be the only equation that we have in this entire problem that will have three variables, or three unknowns, or three letters, characters, hieroglyphics, whatever the heck you are using. All right, so in general, here's the process. First, we have to figure out what the variables we're using are. We have to identify different equations, so we have to build equations and functions based on the information presented to us. We have to graph them. We'll figure out what's called a feasible region. So this feasible region here, that's going to be a shaded area. Please pardon my lack of penmanship. And then once we get the shaded area, we're going to use the vertices or the corner points to figure out what would work best. So let's take a gander at a problem here. We have a manufacturer making two different types of bicycles. We have mountain bikes being built. When we assemble these things, they also have to be painted. Now, based on the type of model of bike, different hours are required for assembling and painting, so on and so on. Then they tell us that the maximum total weekly hours that we are able to do, or to spend on these, are 200 hours. And 108 hours for each type of bike. They give us the profits for each one of these, and they tell us that we're trying to maximize profit. So here's what I like to do. I like to look for the word minimize or maximize. So, bam, right here. We are trying to maximize profit. All right, so that tells me what we're talking about, maximizing profit. So now I need to go through and figure out, well, how exactly am I maximizing the profit? Well, I'm maximizing those by selling different model bikes. I get $25 for profits for model A and for model B. So that's going to come into play. That right there is my objective function. My total profit is going to be $25 for model A, $15 for model B. So what I'm going to do here is I'm going to scroll down to my objective function, and I'm going to say P for profit is going to equal 25x plus 15y. So what I've just done is I've put myself in a situation to now I have to define what's x and what's y. What do these variables even mean? Well, x is going to represent model A. Each bike from model A was $25. Therefore, if I say 25x, that's going to represent model A. Y then is going to be model B. Excellent. All right, so now let's take a look at some other key pieces of information. Let's see, the paint department and assembly department are each limited on the amount of time they can spend. So we have assembly department, 200 hours. And then we have the paint department at 108 hours. Let me change the color of these guys just for consistency's sake. So if I look above in this table, I can start figuring out and building my equations. So one equation is going to deal with assembling. If I know that model A spends 5 hours being assembled, model B is 4 hours being assembled, and I know all total I only have 200 hours to spend on that, I can set a constraint equation. So the parameters I have to stay within of 5x plus 4y is less than or equal to 200. So that right there is going to represent assembly. My other equation that I can write is then going to deal with the paint. Model A spends 2 hours getting painted. Model B spends 3 hours getting painted. All total, I only have 108 hours to paint. So my equation here, my other constraint equation, is going to be 2x plus 3y is less than or equal to 108. Now there's some other equations that they don't explicitly say, but we can kind of go ahead and include in here. And these are the ones that are almost so obvious you don't even think about. And that's going to be x is greater than or equal to 0, and y is greater than or equal to 0. In this scenario, it's not going to make any sense if we have negative bikes being painted or negative bikes being assembled. So we can kind of put that stipulation in there as additional parameters to work with it. All right, let me shrink these down just so they get out of the way a bit. All right, so now it's time to graph. The way these things are written is they are in standard form. Standard form is really, really great if I want to figure out my intercepts. Where does this hit the x-axis? Where does this hit the y-axis? So to do that, I like to go through and use something, I don't know if it's the real term, I like to use what's called the cover-up method. And that's where I simply just cover up one of the values. Now for this as well, I should mention, is I'm going to pretend that this inequality symbol is actually an equal sign. So if I had 5x equals 200, for the first one, I'm going to have an x-intercept at 40. If I did 4y equals 200, I would have a y-intercept at 50. If I do the same thing down here, if 2x is equal to 108, then I have an x-intercept at 54. Over here, 3y equals 108. I can get my x-intercept there as well. So what I'm going to do is I'll start graphing this with my intercepts. Before I get too far, I should probably label my axis. So I'll just count up by 10s, 10, 20, 30, 40. Up here I'm running on a graph, but I'll call that 50. Down here, same thing, 10, 20, 30, 40. Running on a graph, but I'll call that 50. Let me get the objective equation out of the way. All right, so for the first one, we know we have an x-intercept at 40. Boom. And then we have a y-intercept at 50. So right there. Since it's a less than or equal to symbol, it's going to be a solid line. And since it's a less than, we're actually going to be shading underneath this. So I'm just going to put little markings there. All right, for the second one, let me use a different color here. I'll use blue. If I do the same process, get my x-intercept, see 2x equals 108, well, that would be at 54. 54 doesn't show up on the graph, but if it did, it would be right about there. And then we have a y-intercept. Well, 3y equals 108. That means it would be 36. So that would be right about here. Same concept, solid line shading underneath. So I'm going to connect these as best I can, and that's also going to be shaded under. Now the ones that I don't really need to pay too much attention to or fret too much about, because this just kind of naturally happens most of the time, are these two constraints right here, where x and y are both greater than 0. That just tells me I have to shade ahead of the y-axis and above the x-axis. That's really all that means. So right now, after I've graphed everything, I'm going to have this region right here shaded in. This is my feasible region. That means any point anywhere in this region will satisfy both of those equations. Well, I guess technically all four. What we want to do is we want to pay special attention to the vertices. So these little intersection points or corners of my graph. So the different options we have, I'm just going to write this underneath the graph section, is we have a y-intercept up on the y-axis. That was 0, 36. Then we have an x-intercept from that red line. That's 40, 0. I have the origin, which is 0, 0. Obviously, I'm not going to make any profit if I don't produce any bikes, so that's clearly going to be a wrong answer. But this last one here is something that we can easily find with substitution or elimination based on this system of equations that we had over here. So again, if we just pretend that those were equal signs, we could solve that system in a heartbeat. Luckily, I already did. I already took the liberty of doing that. Turns out those intersect at 24, 20. So now when it comes time to maximize this, I'm going to plug these into my objective function. Where are we at here? And just see what happens. So for my point in blue, I would have 0 plus 14 times 36. Or sorry, 15. My apologies. 15 times 36. Let me get my handy dandy calculator. It's 540. Well, 0 plus 540, easy enough. That's $540. All right, at 40, 0, that would be 25 times 40. 25 times 40, let's get our calculator again out. And I realize a lot of us can do this mentally. Is going to be $1,000. So we have 1,000 plus 15 times 0, that's just 0. So that equals a total of 1,000. And then we have the last one, 24 and 20. Well, if I did 25 times 24, that's going to be 600, plus 15 times 20. 15 times 20, that's going to give us 300 for a total of $900. So clearly, the one that maximizes our profit is the red ink option. So to maximize our profit, we need to produce 40 Model A bikes and 0 Model B bikes. Based on the constraints that we've been dealt, that combination is going to give us the most profit possible. And that, ladies and gents, is linear programming. It's a long and arduous process. However, once you get used to the steps, it becomes second nature rather quickly.